Welcome to the first lecture in reinforced concrete design. In this lecture, we will be discussing the material properties of concrete. Concrete is widely used in the construction industry all over the world. It is a composite material consisting of aggregates, sand, cement, and water. All of these can be locally sourced, which is one of the reasons for the popularity of concrete. Due to its composite nature, concrete can be manufactured to meet a variety of special needs, and it can be formed into virtually any shape. Concrete has several advantages, and they include, as we said before, the possibility to cast it into any shape. It is relatively cheap to manufacture, as everything can be locally sourced. Concrete is a durable, fire-resistant and energy-efficient material. To achieve these properties, specification and the method of construction must follow best practice. Codes of practice specify the requirements and provide guidance. The manufacturing of concrete does not require any complex equipment or processes, and it can be easily fabricated on a building site. However, together with these several important advantages, concrete also has disadvantages, and they include low tensile strength. It's about 12 times lower than its compressive strength. As a result, concrete is only used to carry compression. Concrete is also a brittle material. This is an unwanted characteristic, and the design procedures try to mitigate this issue. During the construction stage, concrete is fluid. This volume instability requires the erection of special temporary structures to hold the concrete until it hardens. These structures are called formwork or shuttering, and they're dismounted after the concrete has hardened. Due to low tensile strength and brittleness, concrete is usually used in big, chunky sections. Since it is heavy, this results in a low strength to weight ratio. Let's see what concrete is exactly. Basically, any material made using a cementing medium is called concrete. In civil engineering, concrete is a mixture of the following: cement, water, aggregate, and often chemical admixtures. After mixing, concrete has two distinct states, including the fresh concrete and the hardened concrete state. A chemical reaction, hydration, takes place in the freshly mixed concrete and changes the percentile amounts of the concrete components. Freshly mixed concrete consists of the following: 1% admixtures, 19% water, 9% cement, 29% fine aggregate, and 42% coarse aggregate. When concrete hardens, the water and admixtures disappear, and the percentage of cement, as you can see, grows from 9% to 28%. Concrete is a particle composite, where cement serves as a matrix binding together aggregate particles of different sizes. In the picture, you can see the cross-section of concrete with cement and aggregate. Most cements used in the construction industry are hydraulic cements. These cements require water to settle and harden. The most popular hydraulic cement, which you might have heard of, is Portland cement. There are also non-hydraulic cements, for example, gypsum and lime plaster. These set and harden in contact with air. Gypsum, for example, needs to dry to harden. Lime plaster hardens by reacting with the CO2 in the air. Aggregate used in concrete represents a mixture of fine and coarser particles. The fine aggregates are particles in the range of between 5.6 and 8 millimeters in size. The most typical fine aggregate you'll find is sand. The coarse aggregate has particles in the range of between 10 and 50 millimeters in size, and the most typical is about 20 millimeters. To achieve particle sizes required, aggregate can be crushed. Examples of aggregate include uncrushed gravel, crushed rock, and crushed gravel. Recycled materials like crushed old brick and concrete can also be used as coarse aggregate. Aggregate is required to create a dense, interconnected network within the concrete. This allows for transfer of compressive stresses through multiple paths created by the contact of particles. The higher the number of stress paths created in the network, the smaller the stresses that are transferred. As a result, the interconnectivity of the aggregate network and aggregated properties define important properties in concrete like strength and the modulus of elasticity. After mixing with water, cement begins a hydration process, and this results in the loss of its fluidity. As the hydration reaction continues, cement hardens and the concrete gradually becomes stronger. The diagram on this slide shows a typical development of concrete strength with time. The green dots in the strength curve indicate points at which strength is tested. As you can see, concrete strength is tested on days 3, 7, 14 and 28. Concrete reaches its target strength by the 28th day after mixing. As previously mentioned, concrete is weak in tension and it fails at low tensile stresses. It fails by fracture in a plane normal to the direction of loading. In unconfined compression, concrete fails by developing a network of failure planes parallel to the applied loading. This mode of failure represents tension failure due to the Poisson effect. The compression strength is determined in tests using a special device called a crusher. There are two types of compression tests, and they differ in the type of specimen used. One compression test uses a concrete cube with either a 10 or 15 centimeter side. The other type of test uses a concrete cylinder with a height of 30 centimeters and a diameter of 15 centimeters. As a result of this, the compression strength in the Eurocodes is given as both the cube and cylinder strengths. In these pictures, you can see the results of a concrete cube and cylinder test. The first type of failure is characteristic of the specimen being tested without capping with paraffin, which results in friction between the specimen and the crusher and leads to the confinement of the loaded specimen surfaces. In the other photo, you can see what happens when paraffin capping is present. It eliminates this effect and the failure type looks like the one shown here on the slide. Since concrete is a composite material, its strength is somewhere between the strengths of cement and aggregate, as can be seen here in the diagram. In contrast to the linear stress-strain response exhibited by both cement and aggregate, concrete shows a non-linear stress-strain behaviour after a certain loading. This non-linearity is the result of interaction between aggregate particles and the cement matrix, resulting in the development of microcracks at the aggregate-cement interface. The development and growth of microcracks into cracks causes the deviation away from a straight line. And that's it with regards to the concrete. Join me in the next lecture when we'll look at reinforced concrete and we'll look at the reinforcing materials and how that influences the property of concrete.